Hi, Mick McQuaid here for the third time on day 11 of iste780, Data-Driven Knowledge Discovery. And for this recording, I'd like to talk about dimension reduction methods. And there are two that we'll talk about. Mainly, I'd like to talk about principal components regression, a little bit less about partial least squares, and then a little bit just about working in high dimensions. So let's begin. And to begin with, let's look at this picture here. Because to begin with, I would like to talk about a different topic, which is principal components analysis. This is a topic we'll explore in detail in Chapter 10. It's an unsupervised learning approach, and we're going to use it here as a prelude to regression. And so, so we need to understand it in a sort of very basic, at a basic level. So we have here population and ad spending, and we see we have this cloud of points, and superimposed on it are a couple of lines. This is not the least squares line, by the way. It's a few degrees off of the least squares line. Is my cursor is sort of going where the least squares line is. Well, I'm exaggerating a little bit. It's just a few degrees off. It's like that, and then oops, and then that. So this is similar. This is actually the first principal component. So principal components analysis looks for the dimension of greatest variability. And in this particular set of data with these two variables, the dimension of greatest variability is this represented by this line here. So this is a new axis. So we have this x-axis and y-axis. Principal components analysis gives us a new x-axis, and also, although it's not as important, a new y-axis. This new x-axis is a new variable, which is a linear combination of these variables. We can find a formula for the linear combination here. This is a formula for the linear combination of these variables. And the way that we get this, oh, there's also a picture. Let's look at the picture. The way that we obtain this is we draw lines that are perpendicular to the principal components line. And now we have a value, a single, where before we had two values, population and ad spending. We now have a single value along this axis, a single variable that summarizes those two variables. And that's principal components analysis. Let me give you an example just to close talking about principal components analysis, because this is actually going to be pretty short anyway. Pretend for a second that this is not population and this is not ad spending. This is not the advertising data. Let's pretend that this is height of a person, this is weight of a person, and these dots are all people. So this is a very tall, heavy person. This would be a very short, lightweight person. People on this side of the line are heavier than they are tall. People on this side of the line are taller than they are heavy. So the skinnier people will tend to be down here. The fatter people will tend to be over here. We could now rank everybody on this new dimension, and we could call this dimension. So before we had this dimension height and a dimension weight. This new dimension, which is a summary of people, we could call size, a combination of height and weight. So if we wanted to rank people by size, we could use this linear combination of height and weight. So see how effective that could be for summarizing. There are all kinds of situations where you want a variable to stand in for more than one variable, and that's basically what principal components analysis does. So then we do principal components regression is simply regression on these principal components. Now, in this particular case, in the case of our population and ad, there's a very strong correlation between the first principal component and population and the first principal component and ad spending. These are highly correlated, and we're relying on that. We're relying on there being high correlation. In fact, we're relying on there being high correlation, not only high correlation between them, but we're relying on them. Where in the heck is the thing that I'm looking for? We're making the assumption that, well, I'll just say it. I can't find where it is in the text. We're making the assumption that the line of greatest variability is close to the least squares line. And it happens to be the case here. But it isn't always the case. If that assumption fails, then principal components analysis isn't going to help us develop a better regression. But if it is, then principal components analysis can help us develop a better and more parsimonious model, but not a feature selection model. So this is dimension reduction without diminishing features, because the new features are themselves not the p variables. We're not eliminating the p variables. What we're doing is altering how they're interpreted according to an equation like this. And we can keep doing this from, this happens to be a set where there are only two x's and a y, and we can end up with with everything loaded on this first principal component. We would get very little loading on the second principal component. So see how these are highly correlated. The second principal component, not much correlation at all, which we could have guessed already just by looking at the original picture. There's much less variability in the original picture along the second dimension. And then if we look at this picture of drawing the lines, we see that this is a much narrower, more ellipsoidal shape. This is much closer to being spherical or a square than this shape. It still is. There's still some correlation there, but it's less than this was. And we really see it when we plot the second principal component against ad spending or against population. Imagine looking through this big cloud from the end rather than looking at the big cloud from side to side, and you're seeing sort of, in a sense, a cross-section of the cloud. Okay, now, the other thing is principal components analysis. So here's a case where principal components analysis isn't working that well. Our test MSE, which is in pink here, is fairly high above the as low as it could be. This would be, we would want to get as close to this line as possible. This is the irreducible error. That's the word I was looking for. So it doesn't do that well there. It does better here, and the reason is given here. Let's see. Yeah, the relatively worse performance is a consequence of the fact that the data were generated in such a way that many principal components are required in order to adequately model the response. In contrast, principal components regression will do well in cases where the first few principal components are sufficient to capture most of the variation. So then the question is, how do we figure out how many principal components to use? And the technique that we're going to see here is simply cross-validation. Here we go. So here is, no. Where the heck is it? Okay, I can't find anything today. So, here it is. Here's something about cross-validation. So that's basically the technique that we use to choose M. Oh, here it is, right here. I'm staring right at it. The number of principal components is typically chosen by cross-validation. We should standardize before we do it. Obviously, there's a big difference in the example that I gave you of height and weight. There's a big difference based on the different units that you use, whether you use centimeters or inches or feet for height, or pounds or grams or kilograms or whatever for weight. So yeah, of course you want to standardize, and you want to get into a situation here where cross-validation tells you that there's a lot of dimension reduction. If there's no dimension reduction, which there was in the data on in Figure 620, where is Figure 620? If there's almost no dimension reduction at all, if we're using, where is it? We're using 10 of the 10 components on 11 variables. There's just no point in it. It's the same thing as just doing least squares. Okay, so speaking of least squares, so here's partial least squares. So in contrast to principal components regression, which picked this dotted line here, the line of greatest variability, partial least squares picks the line, does the same thing, but picks the line associated with the least squares, estimate of x on y for um, the first dimension. So it identifies linear combinations of dimensions, but it is supervised. In contrast to principal components, this method is supervised, and it's supervised in the sense that we're looking for we are looking explicitly not for greatest variability, but explicitly for the least squares line. Okay, but we end up fitting a model like the principal components regression model. And it should put the highest weight on variables that are most strongly related to the response. So this is very similar to principal components regression, and gives somewhat similar results, probably less studied and less used than principal components. Okay, and here's some guidance of guidance on partial least squares. It is probably overall no more beneficial than PCR. It's claimed here that it's popular in the field of chemometrics. I believe it's also popular in marketing, but I've seen a lot of examples of it being used in marketing too, and I don't know if they're just not familiar with them or if I'm seeing a non-representative sample. Okay, so high dimensional data. So we have a lot of situations today, and there are some examples given here. I don't think it's very hard to motivate the high dimensional situation. I think this does it right there. Online stuff. That's where we see it. It is certainly seen in other. The Internet of Things, for example, giving us, the Fitbit and having all kinds of measurements that we can take on ourselves, health-related measurements. We can get a very, very large P quite easily in all kinds of network-connected phenomena. Okay, so what are the problems in high dimensions? Well, the first problem is illustrated right here. This is the most basic problem. If n equals p, then the least squares line automatically fits. It doesn't matter if there's no relationship between these. If you have two predictors and n equals 2 observations, you can always draw a straight line through them, irrespective of whether there is any association between x and y or not. And this holds true for additional dimensions. So let's say we were to add a third dimension, a third predictor, z, coming out straight toward us from here, and we add a third point somewhere straight out toward us from here. We can draw a plane between these 3 points, a perfect plane, and it doesn't matter if they're related or not. And in 4 dimensions, we can't easily visualize it, but if we add a fourth observation and a fourth dimension, we can we can't visualize it, but we can construct a 4-dimensional hyperplane between those however many I just said, 4 points, and so on for any dimensionality. And it's not at all unusual in website data to have thousands of dimensions. So if you only have thousands of visitors, then what are you going to do? Any explanation looks just as good as any other explanation. So that's the biggest problem. And they go on about that for a while here. And in general, the more features you include, the lower the training MSE is, and the greater the R squared is. However, also the greater the test MSE is. So we want to minimize this quantity. And this quantity is just based on the training MSE, so it's erroneous. A lot of times you'll see people reporting the R squared, and it makes it sound like they've got a good model, but they are only reporting a good R squared because they threw in a bunch of extra unrelated variables, and the variability just loaded on those variables. And so the training MSE went down. That doesn't mean that they're going to be able to predict anything. And in fact, there's a suggestion here, which I think is really excellent. And this is also a problem. You can't estimate the variance in high dimensions. Where is their advice? So the advice that they give here is really excellent. Interpreting results. It must be here. Yeah. So instead of using R squared, use the MSE or R squared on a test set. So not the R squared on the training data, or the cross-validation errors. So you have to report these kinds of results to have any weight to your predictions. Oh, and we also have to consider the curse of dimensionality. So this picture illustrates the curse of dimensionality. So here is P20, P50, and P2000, and these plots of test MSEs show that they just get bigger and bigger. There's just no way that you can avoid having more variability with more dimensions. So yeah, when P equals 2000, the lasso performed poorly, regardless of the amount of regularization, because of the fact that only 20 of the 2000 features are really associated with the outcome. So this is the curse of dimensionality, and I'll leave you with this. This is a key thing to keep in mind. We have this problem that the more the features that we add to the model, it's not necessarily the case that the better predictor we have, the better model we have. Adding additional signal features that are truly associated with the response will improve the fitted model, but we don't know in advance whether these are truly associated with the test data. We only know that they're associated with the training data. Okay, so now we have a lab in which we will actually let R do most of the work. That's our next for our next trick. And then you also have an exercise 688 to do today, not to turn in, and which presumably I will have posted some solution material for by the time that you see this. Although not necessarily if you look at it in out of sequence. All right, thanks for your attention. Talk to you tomorrow on day 12.